Yeah, there are many fundamental questions that are unanswered and very interesting ones. And I wrote in this slide just a few that I find fascinating, and maybe some of them I work on as well. So, for example, what is the nature of dark matter? That is a big one. So, yeah, well, questions like, is dark energy driving the accelerated expansion of the universe? What's the physics of the very early times and cosmology? Does the equivalence principle hold for quantum systems and so on? There's many, many interesting questions and fundamental physics that don't have answers. And underpinning our difficulties to find answers to these questions is our difficulty actually to unify quantum mechanics and general relativity. I went to a conference a few years ago, and it was all about how can we use quantum experiments for fundamental physics. And many of these fundamental questions came up. And then someone in the audience, a colleague of mine, got up and said, well, but nobody is addressing, kind of the elephant in the room. And what's the elephant in the room? Well, that, we for more than 100 years have tried to unify quantum physics and general relativity, and they're incompatible. So how does that affect all these other interesting questions? And then that's where I think I felt, yes, that is the real interesting question to answer. So this is like the very typical cube that one sees in theoretical physics, but I just a bit designed in a different way, where you have relativity on one axis, so that would be c, the velocity of light, then gravitation on another dimension, that would be the gravitational constant G, and then quantum physics would be h bar. So this cube here, I'm trying to show that, well, we have some pieces of the puzzle. So there are parts of the theories that kind of answer some of the questions or work well in some scales. So, and we have a lot of work done in the last years, in different, pieces of this puzzle, but we don't have the whole picture yet. So quantum field theory in curved spacetime, I would say, is like one of these big pieces of a puzzle. But it doesn't do the whole thing yet. No, so I'll go into why, not in a moment. Okay, so this actually title of this slide, should we quantize gravity or gravitize quantum theory, comes from Roger Penrose. And what he means by that is, should we keep the principles of quantum theory and modify general relativity? That's what we understand more by quantum gravity. Or should we do the contrary, keep the principles of general relativity and modify quantum theory? So I guess, like most people working on the unification, maybe follow the first line of quantizing gravity. But Roger thinks differently, thinks that quantum theory has a problem anyways, which is the measurement problem. So he supports more, let's say, the route of keeping the principles of general relativity and then trying to modify quantum theory to bring them together. Now, we both agree that it's more likely you have to modify both of them. But let's say Roger would always give more priority to general relativity in that sense. So I was writing here in this slide like a few things about both theories. So let's go first to quantum theory. Like same as in classical physics, time is absolute in quantum theory. So clocks tick at the same rate for any observer, independent of its state of motion. And this comes from the theory being invariant under Galilean transformations. So the underpinning transformations are Galilean transformations, just as in classical physics. So in the same, that inherits that space and time are very different notions. The Schrödinger equation treats space and time completely different. It has one derivative in time and two in x. It treats time like a parameter, and then positions can be quantized, and you use operators, which are completely different mathematical structures, no? So then already from there, they would be incompatible with the relativity.
And just for some clarification, quantum theory means quantum mechanics and not quantum field theory.
Yes. I guess because of my background, I use that more when I say I like to use actually more quantum physics, but that I'm just talking about like Schrödinger equation. Fields is like a step more. No. Yes. Well, then in quantum theory, we have the superposition principle. So particles can be in a superposition of two distinguishable locations at a time. And then, well, this is what Roger calls, well, many people call the measurement problem, but in quantum theory, the outcome of measurements is probabilistic. Fundamentally probabilistic. And then when we want to measure, let's say, space or time, we have an uncertainty principle that tells us that if you measure positions very precisely, then you cannot simultaneously measure momentum and so on. Also, it's kind of a bit of a summary of some of these, let's say, fundamental principles of the theory.
Yes.
Then on the other hand, in which way they're different and why are they incompatible? Well, in relativity, time and length are not absolute, are observer dependent. So the underlying transformations in relativity are Lorentz transformations. And if you look at they mix space and time. So let's say the more radical thing I think that we learned from Einstein is that space and time are not different in the way that we understand them in classical physics and also in our experience, right? If you tell anyone space and time are like a bit of the same thing, people would be shocked with that. But that's what Einstein showed us, that they actually belong together in a higher dimensional object, which is space-time. And they're both dependent on the state of the observer. And then you have in relativity, if you have gravity, for example, it curves space-time. And then if you look at two different points in space, you can see that time flows at different rates at different points. So already there you can see that in relativity you have to treat space and time on an equal footing. So let's say equations, if you have that you're having a second derivative in space, you should also have a second derivative in time. So that you can already see how that is already incompatible with quantum theory. And so a little bit also the question of time is at the heart of our difficulties to unify the theory. And then you could think about things. How would you see if a mass is in a superposition of two different locations and then time flowing at different rates? I mean, the Schrödinger equation has only like one derivative in time is one time. You cannot think about such questions yet with the theories that we have currently, no? Another thing, well, just to finish with the slides, like in relativity, we don't have this thing about the outcome of measurements being probabilistic, but it's a deterministic theory in that sense, and we can measure space and time as precise as we want. But well, in my opinion, the most interesting question that we have to answer is what happens when we have a massive superposition where the mass is in a superposition of two different locations in space. And this is something that you cannot answer with quantum field theory in curved spacetime, because, well, I'm going to go more into that later, but the theory assumes that you have sort of a fixed background, so a fixed space-time metric,
yes,
which is a solution of Einstein's equations, but the fields themselves, or the mass, itself doesn't curve it. So you couldn't answer this question. I think this is really an interesting and important question because we know, for example, from the experiments that you can have the electromagnetic field in a superposition. So you can take an electron and put the electron in a superposition, and then you can see that the quantum fields generated are in quantum states. So we were talking about quantum optics, and quantum optics has been, a theory that has been tested in many, many experiments. And we know that the electromagnetic field can be in quantum states. And now the big question is, can gravity also be in a quantum state in this sense? And well, if the mass is very small, well, yes, because the moment that we have, let's say, an atom in a superposition, in a way, the gravitational field produced by the atom is also in a superposition. But I think the big question is more like if that's a stable situation or not, no? And that's where Roger, and I'm going to go more into detail of that, comes in and says, well, you can, but that is a very unstable situation, and gravity collapses the wave function, which would then resolve the measurement problem. And that would explain more like the transition between the classical world and the quantum world. That would explain why we don't see, let's say, this cup in a superposition of here and there and so on. I'm going to talk more about that in a moment. But I guess my point here is that I think this is the most interesting question to answer. And there are good reasons to believe that gravity could act different to the other forces. And that is because gravity is the only one that has an equivalence principle. So there is not an equivalence principle for the others. No, so in the equivalence principle, if you're in a lift and you don't have any way to look at what's happening, so in a box outside, you could not distinguish when you feel an acceleration, if that is because you're in the presence of a gravitational field or just because the box is being accelerated. And that is something that is specific from gravity, and that could distinguish gravity from the other forces. So that is something also that Roger argues that might hint at gravity being fundamentally different. Okay, so I mean, obviously the question is very important per se, but also, as I said, it underpins other very interesting fundamental questions in physics.